Michelle Russo, the Chief Communications Officer of the U.S. Chamber of Commerce, and I am excited to introduce Mike Sarafin, who is the Mission Manager of Artemis at NASA. And I officially want to change my title to Mission Manager. Mike, welcome.
Well, thank you for having us.
You want to go ahead and give us an overview of the program?
Yeah, so we're right up on top of the Artemis 1 mission, so I'll show you a quick video highlight clip, if you could cue that up, just to kind of set some expectations of what we hope to see here in about 2 weeks. So when we roll out of the vehicle assembly building, we move an 11 million pound mobile launch tower and about a 2 million pound rocket all at once out to the launch site. We've already got Artemis 1 at the launch pad, and it's over the flame trench. On day of launch, we'll fuel it with over 600,000 gallons of cryogenic fuel and oxidizer. And when all systems are go, we'll lift off from Launch Complex 39B to start the mission. In just 2 minutes, all the solid propellant in the boosters will be consumed and jettisoned, and then in just 8 minutes, all of that cryogenic fuel will be consumed and the core stage will be jettisoned. At that point, the upper stage in the Orion spacecraft set up for the Translunar Injection maneuver. We get Orion off of battery power onto solar array power, and we commit Orion to the moon just 2 hours into the flight. At that point, the rocket has done its job, and now Orion is on its way outbound to the moon. At its closest point, Orion will be just 62 miles from the surface of the moon, and at its farthest point, it'll be over 250,000 miles away. When we head back to Earth, we'll jettison an important contribution by our European partners, the service module, and we'll set up for our primary objective, which is a high-speed reentry at Mach 32. We'll go subsonic, and then the parachutes will deploy, and Orion will splash down after traveling over 1.3 million miles in the Pacific Ocean within viewing distance of our recovery team on a U.S. Navy ship with NASA personnel on board. We'll keep the spacecraft powered up for about 2 hours post-splashdown to understand how much heat has soaked back into the cabin for astronauts that'll fly on subsequent missions. We'll recover the capsule, and then we'll set up to fly astronauts on the very next mission. So that's a few of the highlights of what you can expect on Artemis 1. In terms of our mission priorities, we've got 4 mission priorities. Number 1 is to demonstrate the vehicle's reentry at lunar reentry conditions. When you fly to low Earth orbit, you come back at 17,500 miles an hour, or Mach 25. When we come back from the moon on a direct reentry, we're going to come back at 24,500 miles an hour, or Mach 32. So we're going to have Mach 32 astronauts on future missions when they come back. In order to achieve that high-speed reentry, we need the rocket to do its job. We need all that chemical energy stored in the solid boosters and in the liquid core stage and in the liquid upper stage converted to kinetic and potential energy that is then taken out when we hit the Earth's atmosphere, again at Mach 32, through the use of an ablative heat shield. There's no facility here on Earth that's capable of replicating those high-speed reentry conditions, which is why we need to test this heat shield. It's a brand new design and why we're setting up for an uncrewed test flight. Priority number 2 is to operate the systems in the flight environment. When we launch, we're going to fly up through the period of maximum dynamic pressure. We got a 32-story tall rocket. It needs to go through all these jettisons of the solid boosters, the solar array fairings. We'll jettison the launch abort system. We'll jettison the core stage. We'll convert Orion from battery power to solar array power. We'll fly out through the micrometeoroid and orbital debris environment encircling the Earth. We'll fly out through the Earth's Van Allen radiation belts, which are high periods of, or high areas of radiation concentration. We'll transit out beyond the Earth's magnetic field. We'll transit out beyond the tracking and data relay satellites that are used for low Earth orbit and terrestrial users to communicate. We'll transit past the global positioning navigation system that is used, again, for low Earth orbit and terrestrial users to navigate. So we're going to use radiometric tracking, the Deep Space Network, for command and control navigation. We're also going to use star trackers and optical navigation. And we're going to operate the spacecraft in that deep space flight environment for an extended period of time before bringing it home. That's priority number 2. Priority number 3 is to simply retrieve the spacecraft. By getting the spacecraft back, we get all the data that's recorded on board in engineering flight instrumentation that we did not telemeter to the ground during the mission. We also get the high precision avionics that are on board for programmatic cost savings and reuse. And then we get the structure of the crew module back for engineering testing post-flight as part of an engineering test program. And then our 4th priority is what I like to call bonus objectives. It is to accomplish payload objectives. It's to share the mission with each and every one of you. We're going to provide outreach. We're going to share remarkable images. We're going to share images of Orion looking down at solar array wing with the crew module in the foreground, the moon in the background, and then the Earth 250,000 miles away. And we're going to share that with each and every one of you. We're going to encourage young men, young women to enter the fields of engineering, science, technology, engineering, and math. And we're also going to conduct payload science through understanding the radiation environment. We're going to deploy 10 CubeSats. We're going to round trip payloads in Orion to help us understand what that environment is like for future astronauts. So those are a few things that you can expect on Artemis 1, and we're right up on top of that mission, and we're excited to share it with you.
So, Mike, you gave us a small sense of, or a nice top-line sense of what goes into launching what NASA is calling the most powerful rocket. It's a massive undertaking. So far, we've had a couple delays with hydrogen leaks. You know, I like to say there's two types of people in the world. There's the type that gets really annoyed when the mechanics and engineers want to check out and make sure the plane is safe before it takes off, and then there's me. I say take your time and get this right. Give the audience a sense of what goes into that go, no-go decision.
Well, there's an extraordinary amount of planning. We look at each subsystem, whether it's the communication systems, the navigation systems, the propulsion systems, the electrical systems. You can go down the checklist. And we break those down into individual go, no-go criteria. We understand the levels of redundancy, we understand the decision gates, and then we plan ahead in the terms of launch commit criteria, flight rules, and what we call recovery decision criteria. We plan as many of those decisions as we can ahead of time, partly because we want the operation to go smoothly if something unusual happens, but also if something unusual happens that's outside of what we've agreed to, at least we have a framework to start from. And then we rely on our engineering expertise. So defining the roles and responsibilities, defining your plans, understanding the system capabilities, having a test program where you get that information, and then rolling it into the mission, and the mission plan is all part of it. And we've spent months and months and months to get ready for this mission, and we'll see what it brings.
You mentioned one of the goals being spacecraft retrieval. Are some of the components of the rocket reusable? What's the whole philosophy around having cutting-edge technology, the investment, and then the long-term return on that investment?
Yeah, it's a great question. The crew module and the avionics on board is the only element that we get back. We made a purposeful design decision to bias the rocket towards performance. That's as much performance, as much mass as we can throw towards the moon, so we can deliver crew and cargo and supplies as far as we can. If we were to incorporate reusability in the boosters and the core stage, that is performance you're holding back that you would normally be able to use going to the moon. So you have to have propellant that you hold back to vector the vehicle back to somewhere on the ground. You also have to have recovery systems, whether it's landing gear or parachutes or some other subassembly. So you're adding weight just to recover this thing. So we, again, have a purposeful performance bias system here. And this thing is designed purposefully to deliver as much mass and crew and cargo as far as we can.
Let's go back to the Space Launch System being billed as what NASA calls the world's most powerful rocket. What makes it so?
Well, it's 15% more powerful than the Saturn V. It produces 8.8 million pounds of thrust at liftoff. And that's just the initial design of it. We have an upgrade coming that will allow us to take a vehicle that's capable of delivering roughly 70 metric tons of crew and cargo to low Earth orbit to 105 metric tons. So we'll be able to deliver not only the Orion capsule and crew to the point of translunar injection, but we'll also be able to deliver large cargo elements for the gateway. The International Habitation Module is a great example. We will deliver that in one shot, uniquely in one shot, with our astronauts and send them out to the moon. And that's what makes this the Mega Moon rocket.
So you're touching on this super heavy lift capability concept for this mission. What impact will that have going forward for having this capability now and testing it?
Having a national capability that you can partner in any number of ways has almost innumerable benefits. You could partner to deliver, like the example is deliver the International Habitation Module or the Gateway on future missions. You could stage large amounts of supplies for your astronauts in the vicinity of the moon or very complex missions. You can deliver any number of large cargo elements, and that gives you flexibility to kind of build out an architecture. And that architecture then becomes the foundation where there's many other things that can leverage off of it. It's a model not unlike the International Space Station. It took a while to build the core of the International Space Station, but then we added on a whole host of payload and partner capabilities, science capabilities, the alpha magnetic spectrometer, and you just build out and out and out from there. So as you add your core capabilities and power systems and additional systems that can basically leverage that, it becomes the beginnings of an architecture, and having the fundamentals of having a deep space transportation system that allows you to deliver that to the point of translunar injection allows you to take that next step.
Okay. So at the U.S. Chamber, we represent businesses large and small, and we fundamentally believe that the relationship between government and business is critical to improving society. And the space program is a great example of public-private partnerships. And I would just love to hear you tell the audience a little bit more about the important role the private sector has played in getting to this point.
Yeah, absolutely. You know, we have a very broad supply base in the United States. We're very proud of our supply base. It reaches all 50 states. While we do have a number of prime contractors, their supply base is deep and far across the United States. And we even have a supply base that reaches into Europe through our European partners, some of which then reach back to the United States to supply components for their contributions. So when you look at how the space program reaches people, it always strikes me. You go on a number of the supplier visits that I've been to, some of them, they specialize in one thing, machining titanium, or you know, making parachute systems and detonation cords. And when you see how highly specialized they are, it is a combination of engineering and art. It's craftsmanship that they have, and they take great pride in being part of the American space program and their contribution in it. And they share that heritage, they share that technology with other users, and that just kind of creates its own ecosystem, and it's a remarkable thing to see. But there's also that element of pride. There's also that element of inspiration to that next generation. And I grew up in a small rural area in upstate New York where there weren't that many opportunities up there. And you see a small supplier that's supplying these precision components, and you think that the only place you can do that are in these major aerospace areas. And then you start to realize that this ecosystem is much bigger than what you normally see or is normally talked about. So it reaches wide and far, and that's a huge benefit.
So last question. It's at the beginning of a school year, so we're posting pictures or seeing lots of pictures of kids holding signs about what grade they're in and what they want to be when they grow up. And you see astronaut, but there's massive careers in space. And how do we make sure we do what you referenced earlier in your remarks about encouraging kids to pursue these types of careers so that we can take our space exploration to the next level?
Yeah, you know, I'm asked frequently about how do I get involved in NASA and how do I find a career there. And, you know, it's number one, put in the work. You got to put in the work from a schooling standpoint. Go get a bachelor's degree in science, technology, engineering, and math. And then get out there and maybe make a mistake. Don't be afraid to make mistakes. I see young men and women that are sometimes paralyzed with a decision about taking a job because it might not be the optimal job. You never know where those working relationships are going to lead. You never know what you're going to learn. And sometimes learning that is not the right job for me. I don't like testing. I don't like development. I love operations. That is a very valuable thing. And the sooner you learn that, the sooner you learn who you are and the sooner you're able to contribute. So one of the key pieces of advice that I give is get out there, don't be afraid to make mistakes, and learn from it.
Well, I think the whole space program is such an exemplary example of that. And thank you for your time today. We hope the audience learned a little bit more about this exciting new mission that's about to blast off soon.
You're welcome. Thank you for being fantastic hosts.
Thanks.